Hi everybody! A few months ago, I created a tutorial for generating a simple two-dimensional grid, and recently, I thought it would definitely be useful if we could do the same as a projection into the third dimension. The algorithm for the grid itself will remain the same, but we will add elements like a 3D camera, projected UVs, and so on. Let's take a look at how such a shader works. As usual, I begin with creating the scene, color rect, and the material with a shader. This time we are not working with a texture, so color rect will suffice. Okay, right click, create new scene. Let's call it 3D grid. Okay, and okay. Right click, add child node, color rect, and I will set the usual dimensions, which should be 600 by 400, and the material, shader material, click new shader, canvas item, 3D grid GD shader, change the folder to shaders and create, and click to open in the editor. Okay, I will delete everything that is not needed, so only the fragment function will remain. Let's delete vertex and white. Alright, as I mentioned, the shader will be based on the two-dimensional grid that I created in another video, so I will rewrite part of the code as I used it then. This will include the function for rendering the grid itself, and then the usual beginning of the fragment function. But first, I will add the necessary uniform parameters. Uniform vec2 resolution equals vec2 600 by 400. This is simply to match our current resolution of the color rect, and we will use it to recalculate the aspect ratio, so the grid is composed of squares, not rectangles. And second one, uniform vec3 line color with a hint source color, and the initial value 0.2, 0.3 and 0.5. This is taken from the original shader code exactly, so it means that we are creating RG and RGB color. Well, this hint will help the inspector show this nice color picker, and this is the initial value. Okay, and finally uniform float thickness of the line with a hint range and the default value 2. And I think the range was from 0.1 to 10. Very well. Now the draw grid function. To explain why I used cosine and max, I recommend watching the previous video, the URL of which can be found in the description of this video. Let's do it here. Float draw grid vec2 UV as an input parameter, and we need to define the grid UV. That would be the mentioned cosine function applied on UV multiplied by tau, which is a double pi, and return, typing too fast, max of grid UV x and grid UV y. Great. Alright, now for the new things. We will need a function that projects a two-dimensional point into 3 dimensions using the camera's position. This means the function will have as input parameters the UV coordinates of the camera and then its height above the surface of the projected plane. Let's write this function, but first we'll need two uniform parameters. I mentioned the camera height, so we will add this value as a uniform parameter, and we will also need the FOV, field of vision, for the camera, which will be the second one. Let's do it. Uniform float height with a hint range and initial value 1.5. The hint range was from 0.1 to 10, and uniform float FOV, hint range, and I think I set it to 90 degrees, and the range was from 30 to 180 degrees. Okay, and now the function itself. Let's call it project UV, and it will return vector 3. Vec 3 project UV sorry, project UV initial input parameters vector 2 camera, as I said, the camera position and the camera height, which I will simply call world Y because we'll be converting that to the world coordinates. Let me write the formula, which I write first, and then I will give it a short explanation. Is world Y multiplied by camera X divided by camera Y. It's very similar to our recalculation of the aspect ratio. Second one is world Z. That would be again world Y, but this time divided by camera Y multiplied by 10 trigonometric function of 0.5 plus the mentioned FOV multiplied by, no, not plus, but multiplication. And the value of FOV is in degrees, but the trigonometric functions work with radians, so we need to recalculate that to radians, which is simple, just multiplied by pi divided by 180. Okay, and finally I will return the vector 3, which is composed of these three components: vec 3, world X, world Y, and world Z. Okay, it seems there is a typo, not dot by underscore. Now it should be correct. So this gives us the projected UV whose X and Z coordinates I will send as parameters to the draw grid function. Y constant is Y is constant in this case, but if we wanted a different camera movement than forward, we would need to take that into account as well. Okay, and now the code. I will start by projecting UV coordinates into 3D using our new function right here in the fragment function. So float world Y would be the height from the uniform parameters, and vector 2 projected UV is the result of project UV, where we use the UV coordinates and the world Y. Yes, we know that project UV returns vector 3, but as I said, we will use only the X and Z coordinates, so it is in fact the result is vector 2. So we have the new coordinates and we need to create a grid from them, which repeats infinitely in the XZ plane. As we know from the original video, the fract function is well suited for this, as it always returns a value between 0 and 1, and the result will repeat periodically. Let's do it here. Vec2 grid would be, as mentioned, fract function applied on the projected UV Okay. And semicolon. From the result, we will subtract 0.5 like this, just to avoid having a vertical line in the middle, which doesn't look good. But of course, if you prefer to keep this vertical line, you can omit this subtraction. Very well. And finally, the calculation of the resulting pixel color. Just like we did in the first video with the two-dimensional grid, we will include the line thickness and its color in the calculation. Then I will smooth it all out using the smooth step function. The float line thickness will be our thickness from the uniform parameters divided by resolution dot y. So we just take the current resolution into account. And the color, vector 3 color would be, as I said, smooth step to make it look nice and without too many artifacts, minus line thickness to define the range for the smoothing. The second edge would be simply 1, and the value is the result of our function draw grid with the new coordinates taken from the grid vector. And of course we need to multiply the result by the line color predefined in the uniform parameters as well. Okay, what's left? Let's assign the result to the internal variable color, which is vector 4. So it would be color and 1 for the alpha channel. Vector. Wait for it. Okay, we definitely have something here. It is a nice projection into the third dimension. However, it still needs a few improvements. The camera should smoothly move forward and the center of the effect should fade into darkness. Let's address the movement first. We will need a uniform parameter for the speed. Right here, uniform float speed with a hint range and initial value 4. And let's make it from 0 to 10, so we will be able to fully stop the movement if necessary. Now we will set the camera movement vector over time according to this. As I mentioned, it will be a forward movement, so the x component of the vector can be set to 0. Okay, I think I can do it here. Vec2 direction is vec2 and 0 for the x component, as I said, and time by speed for the y. And we will add the direction to our projected coordinates. Where is it? Here. So grid here. Projected UV plus direction. Wait. Yeah, it's moving. And we immediately see a problem because the sailing moves in the opposite direction to the floor. We can easily fix this because we know that the origin of the coordinates 0, 0 is at the center of this rectangle. So if UVY is less than 0, we multiply the result by -1. The sine function is useful for this, as it returns 1 for positive numbers and -1 for negative numbers. So let's do it here, multiplied by sine of uv dot y. Wait. Great. I think the grid will be more visible if we increase the thickness to the maximum, which is 10. In the inspector, okay, definitely better. Now we need to address the center so that the lights fade with the distance. I will add the parameter fade factor. But I think it's still a little bit flickering here, so let me stop that, moving the speed to 0. It should be better for our eyes. Okay, uniform float fade factor, again with a int range, and the initial value I'll set to 10, and the range should be from 1 to, let's try 50. Okay, and we'll use this in the calculation, incorporating the length of the projected point into 3D, so we darken only what is truly far away. Let's get back to the fragment function and calculate the fade. Float fade is minimum of 1.5 and the power function 1.2 to the power of our fade factor minus, as I said, the length of the projected UV point, and semicolon. And of course we need to calculate that, so I will multiply the resulting color by this value, fade. Yeah, here it is. We are almost done, but we can make one more improvement, actually two. It might happen that the grid isn't displayed too brightly, so we'll multiply the resulting color by a brightness value. First, though, we need to add this brightness parameter. Okay, uniform float brightness, int range, and initial value 2. I'll make it from 0, semicolon, from 0.1 to 4. Okay, and the usual multiplication in the color assignment multiplied by brightness. Yeah, it's brighter. And now the second thing. Let me just start the movement again. I'm not sure how it looks on YouTube, but it can happen that the motion of such a grid causes an unwanted flickering effect, as I mentioned, especially if the line thickness is too low. This can be partially addressed using a technique called supersampling. Essentially, this means we render several identical grids that are offset by 1 or a few pixels from each other. First, we'll set the number of such a supersampling grids using uniform parameter, but I will definitely just stop it again. Okay, let's do it here. We have so many uniform parameters, but I think this one is the last one. Sample into range, and it should start at 10 from 1 to 20, and the step is 1 because there's definitely nothing like partial supersampling layers. Okay, and now we'll need to perform the rendering in the loop. Let's do it. First, we'll calculate this offset based on the current resolution. Since it will be the same for all iterations, we'll do this calculation before the loop. Right here. Float supersize is supersample from the uniform parameters, and again divided by the resolution y, just like we did for the line thickness. And now the loop. Since after each iteration we add the current colors to the total result, I will create a new vector for that result and assign it to the color variable at the end. So after setting up the direction, and I think that I should change the order of these two lines because the second one will be inside the loop right here. Okay, so supersize, direction, and now vector 3 result. Let's start at vector 3 0 black color. And finally, let's just do it at this moment. Instead of color, we will use the result right here. Nothing should be displayed now. And let's write our loop. So it would be here. For float I from 0, I less than super sample, and I is increased by 1. I will just put all these lines into the loop body and change the indentation by selecting all of them and pressing the tab key. Okay, and as you can see, I enclosed everything which cannot be compiled now because some variables are defined inside the loop and cannot be used outside of it. Let's fix that. So we need to do this. Result would be increased by color multiplied by fade multiplied by brightness, just like we do it here, but because the fade is defined inside the loop, we cannot do it outside that. And here I will simply use only the result. Let's wait. Okay, if I run it now, we can see that the flickering is still there. That's because our algorithm is not complete. So what's missing? In each iteration, we need to shift the grid by a different amount. Otherwise, the colors will add up, resulting in what we can see now. Everything is white. So let's do this. At the start of the loop, I will define vector2 called super offset. That would be vector2 of 0 and I, which is defined in the loop and is increased in each iteration multiplied by supersize. Okay, and of course we need to use that in our calculation. So in here projected UV plus direction plus the super offset. Okay, and because some parts of the grid overlap, we will use average color values. So we divide the result by the number of iterations outside the cycle, of course. Result would be divided by the number super sample. Okay, let's start it again. Great. I think we can set, it works. This supersampling technique is one way to simulate the smoothing of visual artifacts, also known as anti-aliasing. Of course, it's not suitable for all situations, and there are other more effective algorithms as well, but that's a topic for another time. And the very last thing, what if we wanted to display only the bottom part of the grid? Because maybe we want to have sky or something like distant mountains at the top. The solution is very simple. We'll perform the entire calculation only when uv.y is positive. So right here, if uv.y is greater than 0, then do all of this. Great. This is it. Thank you for watching. Perhaps such an effect will come in handy as a background in a game featuring futuristic races inspired by the movie Tron. In this form, it's a basic solution that can be improved in various ways, but that's something everyone can explore on their own. For now, take care, good luck with your projects, and see you in the next video.